Hi everyone, it's nice to meet you and thank you for watching this presentation of our work on the inverse simulation of light. I'll explain to you in a few moments what that actually means and why it's useful, but I'll begin with a few words about myself. I'm an assistant prof leading the realistic graphics lab at EPFL. And what my group does is to develop algorithms which can generate photorealistic images using a computer simulation of light. And these kinds of images are known as physically based renderings because they're made by simulating physics quite carefully. And this is useful for many applications where we might want to know exactly what something is going to look like before we create it. So think of an architect or a product designer, for example. And these methods are, of course, also used widely in the movie industry, and we collaborate with many companies in this area. Now, one thing that's worth mentioning is that physically based rendering tends to be kind of slow. So something like 8 hours of computation time for one image is perfectly normal. And what's really remarkable is that despite this cost, these algorithms are now used everywhere around us. And so when you go to the movie theater and you see these incredible imaginary worlds and photorealistic detail, there are actually large compute clusters racking up millennia worth of computation time behind the scenes. But renderings are often much less obvious, for instance, in a catalog containing shoes or furniture. And what some of you probably haven't realized is that when you look at your typical IKEA catalog, over 2/3 of the images are actually renderings and not photographs. And the company does say so publicly. Let's talk briefly about the problem that a rendering algorithm must solve. And full disclaimer, this is actually a picture that I took on my balcony to illustrate the important phenomena. So here we have light that's streaming in from the left side. It hits the red book and then transfers some of this red color to other objects. We have sharp metallic reflections and the absence of light due to shadowing. Some of the light goes through this milk pitcher and it gets focused into these complex patterns called caustics. Light that goes into the pitcher of milk interacts with the fat bubbles that make up the milk, and it kind of bounces around back and forth before coming out somewhere completely else. And this is what gives milk its kind of typical glow. If we didn't simulate that, it would not look very appetizing in a rendered image. So I think the main takeaway message from this slide is that all of the objects talk to each other through light, and that's a really important effect that we have to simulate for realism. It also means that if I, for instance, move any part of this image just a little bit, it could in principle affect any other part of the image. And that's one of the reasons why these simulations are quite costly. But if you remember the title of the talk, I was actually going to talk about inverse rendering and not ordinary rendering. And so that means we want to go into the opposite direction. So an ordinary rendering algorithm is given a description of the world, things like the position and the shape and materials of objects. And then it does some calculation, which is described here by a function f of x, and out comes in the end an image that accounts for all of these complex effects that we have seen. And an inverse renderer actually goes the other way. So it's given one or more input photographs, and then somehow it has to come up with a description of this virtual world, which is consistent with the images. And that really seems like a much more challenging problem, partly because of this interreflection. And just to give you an idea, in the previous example of the photograph on my balcony, it would mean that we would somehow need to understand that there is a red book, which is being reflected in the laptop. Or otherwise, we might sort of get confused and think that this surface has some red patches on its surface, which is, of course, not the case. And so the question then is, how could we go about constructing an inverse for something that's this complex? And that brings us to the topic of neural networks. Now, one thing I must stress is that we don't actually use neural networks, but it's worth taking a brief look at why they work so well. So at their core, neural networks are really just a simple sequence of arithmetic operations with many parameters that we can tweak to influence their behavior. And one of the key pieces of technology that enables all of this is reverse mode automatic differentiation, also known as backpropagation. And so that's the algorithm which gives us gradients that allow us to tweak all the parameters in just the right way to solve a challenging problem. And so now let's take a look at rendering algorithms through that lens. So here we also have many parameters. We have maybe 10 or 100 million input parameters. There is some calculation that produces an output. And so the question then is, well, maybe we can also similarly differentiate these the underlying simulation, which gives us parameter derivatives. Now, what's needed to complete the picture here is that we require some kind of an objective. So this is, of course, a little bit naive, but in principle, we could say, well, maybe I don't like the picture of this bathroom. I would rather like it to look like something else. So we compute some kind of a difference that gives us a loss, one number basically that tells us how close we are. And then we differentiate all of the input scene parameters. And what that tells us is basically a direction of steepest ascent in this high dimensional parameter space that will improve this loss if we walk into that direction. So all of this is incredibly flexible. You could think of all kinds of loss functions and simulations. Really, the only important thing is that things are differentiable. Okay, so let's try and get some intuition about these derivatives. Here I'm showing ones for a Rubik's Cube where I'm differentiating the front faces. You can immediately see the global nature of light because that's actually also changing the reflection of the cube. Or I can rotate the top part of the cube. I can translate it. You can see that that has an effect now on the shadows, or I can translate the light source. Also, that has a big effect on the shadows. Now, what is all of that actually useful for? Well, imagine that you're given pictures of an object. So here we have a starfish, and our goal is to reconstruct that. Let's say we don't have access to the actual 3D geometry. What you could do then is to start from kind of an initial guess. So let's say this is our initial guess. We have sort of the right topology, but the colors and the details of the shape are incorrect. And then we would simply take differences of these two images, differentiate them, and then try and make them look closer and closer to each other by taking gradient steps. And that actually works. So you can see it here. We increasingly reconstruct the shape and the color. And then over time, even the subtle details come out. So the algorithm is now pushing out the little bumps of the starfish. Now, it's fairly easy in this case because the target is actually also a rendered image. But this idea also works for photographs. And so here we're reconstructing a pair from photographs of a pair that we took in the lab, starting from a sort of a generic green blob, and works really just in the same way. And the longer we run it, the more crisp the reconstruction becomes. All right, so here we are reconstructing something that's directly visible. But one really interesting thing about light is that the indirect effects that it has on objects. And so here's an example of things you can do with that. We have a light source that's illuminating a glass slab, and the glass slab is initially flat. Nothing particular happens, but we could actually change the height at different places of this glass slab to reconstruct, to focus light into a certain pattern. And so what we're doing here is to optimize the height structure of this glass slab so that it focuses light into a picture of the great wave. And here you can see that the surface is now a little bit rough, so it's not perfectly smooth anymore. But these height variations have been very carefully optimized so that this picture is reconstructed. How does all of this work under the hood? Well, the key idea is to record a graph of all of the computation. That means things like additions, multiplications, and so on. And that graph is then traversed in reverse in a second phase, which gives us all of the derivatives at once, even if there are millions of them. Now, in practice, though, this graph becomes incredibly large for the kinds of simulations that we're interested in, actually much larger than what you can see here. There's just no way for me to include a 100 megabyte PDF file in here without crashing the presentation software. And because of that, normally you'd use a framework like PyTorch or TensorFlow to do the differentiation, but that's really not applicable anymore because it doesn't scale to such large problems. And so we've started building our own systems for large-scale differentiation, which involves things like graph simplification and just-in-time compilation to optimized kernels that run on the GPU. And that brings us to some of the current challenges. So differentiable rendering is really quite hard. It's certainly much harder than ordinary rendering. And the first part is that the computation underneath is just messy. You have light that's being reflected by object. It goes all over the place. So it's very different in flavor to the kinds of computations that you have in neural network land, like convolutions or matrix multiplications that are very regular. One interesting aspect is that we have visibility, and visibility changes in the real world. And so that actually introduces discontinuities. And that means if you just naively differentiate your rendering algorithm, you're actually not going to get the right results. So you have to be more careful about that. Also, just having derivatives doesn't necessarily mean that you can solve challenging problems. You could always get stuck in a local minimum, and developing parameterizations that are more robust in that setting is also a really interesting problem. And then last but not least, you probably need to do a few of these gradient steps, maybe hundreds, thousands, or tens of thousands. So it has to be fast. And currently, the methods that are being used are quite slow. So improving the scalability of differentiable rendering is quite important. So this is all really a brand new topic, physically based differentiable rendering. And I would say that most of the interesting work has happened in the last 1.5 years. And that actually makes this a really exciting time in computer graphics, because in the past, we've been very focused on visual effects and movies, but suddenly there are lots of interesting applications in other areas. Just one example that I'll give you is architecture. So in a building, it's usually very bright close to the windows, and it's too dark on the inside of the building. And that means we have to add extra electric lighting. And there's a whole subfield of architecture where people try to improve buildings to make better use of naturally available sunlight so that they don't need that much electric lighting. And with our tools, we can phrase this as an optimization problem and just differentiate the whole building with respect to an optimization goal that's specified by the architect. On a completely unrelated note, one thing that we also do in my lab is to measure real-world materials and build mathematical models that enable us to improve their realism and rendering. And we have a state-of-the-art measurement lab, including a robot that you can see here that kind of very rapidly moves around an object to scan it and bring it into the virtual world so that we can check how well we're doing. And that gives you a brief flavor of some of the fun things in the area of computer graphics that we do here at EPFL. If you have any questions, please don't hesitate to contact me, and my email is shown on the top here of this slide. Thank you.